So we're looking at different techniques of finding the derivative. So now that we don't have to use that precise definition of a derivative, that limit as h goes to 0 of f of x plus h minus f of x all over h. Hopefully you guys are experts at that, but it could take a long time. And so these are tricks to make our life so much easier. And so these were the rules that we started to look at yesterday, and we started to prove some of them. Actually, I think we proved all of these. The one that I just boxed up here is the one that we're going to be using a lot, well, I guess with all of these. So I wanted to, maybe let's go through another rule, and that is our product rule. And yesterday we ended with an example where I said, no, if we have a product of two functions, unfortunately, we just can't take the derivative of the first times the derivative of the second. It just doesn't work. And I showed an example why that wouldn't work. And so let's look at the product rule. So let's say that f of x is equal to two functions, u of x and v of x times v of x. U of x and v of x are both differentiable. Then, when we take the derivative of this, f prime of x, this is going to equal the derivative of the first, so u prime of x, times the second function, v of x, plus the first function, u of x, times v prime of x. So my notation, it might look a little different than what your book did. So I put in the u of x like a function, f of x like a function. Your book said maybe I think f is equal to, oops, f is equal to, I can always just pull that up. They said both u and v are differentiable, which I said they're both differentiable. Then so their product is uv, and they said the derivative d of over dx, which is just another way of writing this, of our function that we're taking the derivative of, which is u times v, this is equal to u dv over dx plus du over dx times v. So just different notation. But same thing. So we got Leibniz and Newton's notation going on here. And so let me just kind of talk this through a little bit. And when I learned this and how I have been teaching it, I've always taught the product rules, the derivative of the first times the second, plus the first times the derivative of the second. Your book here does it flipped, which there's nothing wrong with that because of the commutative property. If I add two things together, it doesn't matter what way I add them, and it doesn't matter what way I multiply two things. A times B is B times A. So they technically mean the exact same thing, but that's just how I learned it and how it just kind of hammers out in my head. Derivative of the first times the second plus the first times the derivative of the second. Okay, so let me just kind of walk through what this is saying. So they had said instead of naming their function something else, f of x, all they were saying is let's take this derivative, d dx. This is saying we're taking the derivative of this piece, u times v. So they haven't taken the derivative yet. And then after, this is equal to, so u is our first function. So we haven't done anything with our first function, whatever that is, and what will be defined when we're giving it. dv dx, this is the derivative of the second function. And u dx, that's the derivative of the first. And that v is just the original second function without taking the derivative yet, or not taking the derivative. Okay, so I can go through and we can prove this. It actually falls out really nicely if you understand what value you're going to add to it. So, you know, sometimes we looked at limits and we got that indeterminate form, infinity over infinity, and we didn't like that, or 0 over 0. But if we multiplied by that fancy one, it made it all turn out so nicely when we did the algebra so that we knew what the limit was. Well, same sort of idea here. Sometimes I was thinking we'd like to add fancy zeros. So instead of just adding 0 to something, we say, let's add b plus negative b. Well, that's just 0, right? And so we're going to do that to manipulate this so that it falls out really nicely. Okay, so just so that you get into proofs and you see them more, and more instructors might prefer them than other instructors. I'm not too hot on them, but I think that it is important to see them sometimes. Also, if you are into mathematics and you're thinking about doing a degree in mathematics, I didn't realize this until I got into my upper division math, but a lot of it was just proving in theory, and it was something that I did not like. Maybe because it was up there for me. Anyways, point being said, I made it through what I didn't like to get to where I'm like what I like, which I'm doing right now, teaching you guys mathematics. Okay, that being said, we're going to take the derivative of, and I'm just going to write it how they do, u times v. Well, unfortunately, we're going to go through and we're going to look really quickly at this limit, the precise definition of this. And so the precise definition says, well, we're going to look at u of x plus h, v of x plus h. So we're just going in and plugging in x plus h wherever we see an x in our original function, minus the u of x and the v of x. So again, u of x and v of x are just functions that's not times x. And so that's why sometimes the book just used u and v, but those are functions in terms of x, all over h. Okay, so this is where we want to add 0. But our 0 is going to be where it is negative u of x plus h times v of x plus u of x plus h times v of x. So I'm just going to go in and add this funky 0 in here into my equation. I hate it when it says that. Into my equation up here. So the whole point of doing that is so that I can do some factoring by grouping and manipulate it to look like our difference quotient, that limit of our difference quotient, which we know is the equivalent to the derivative. And so doing this, we get the limit as h is approaching 0 of this first piece, this u of x plus h, minus what I just was adding in, this funky 0, negative u x plus h v of x plus u of x plus h v of x minus my u of x times v of x and this is all over RH. So let's factor by grouping. In our numerator.
Can I ask where the v and then the x plus h, is that what is getting plugged into? The 0?
This is our 0. This in blue is our fancy 0 that we're plugging in here, that we're adding to our numerator.
Oh, to the v x plus h, because it just disappeared in the second part.
Oops, you're right. So let me
Yeah.
pull that down here. So this should be down here. Thank you for catching that. Here's my.
No problem.
Actually, so I'm going to just squeeze it in over here. So this has this v still in here times x plus h. I just wrote it in the, and then still have that limit. Yay, I would have noticed that on the next piece when I was trying to do that factoring by grouping, and so you just saved me a lot of heartache and your class some time. So looking at this, we want to factor by grouping. So again, factoring by grouping is something that we do sometimes, like when we were completing the square, we manipulated things so we could factor by grouping. No, maybe not that one. That's not what I'm talking about, but that's okay. Anyways, here, notice what we have in common. We have this ux plus h in common with the first two pieces. So let's pull that out of those two pieces. And so if we pull that out of those two pieces, we have this u all times x plus h times what we're left with. So what we're left with is this v of x plus h. If I pull them out of that, I pull that rectangle out, minus, and if I pull this u of x plus h out, I'm left with vx. And then over here, let's pull out, again, we have to look at what they have in common. So if you look at what's in common in the last two groupings, notice they both have a vx in common. So for those two pieces, we're going to pull out a positive vx. And I think I did something wrong. No. Okay, let me just keep going. Pulling out the vx, I am having left with, sometimes I question myself, u of x plus h, and then minus u of x. So this is all over h, right? It's all over h. Doesn't this kind of look familiar, what's in black? And if this is all over h, we can rewrite this as two separate fractions, right? Because it's a single term, we could just write this one over h and this one over h. Common denominator, we could rewrite it as 1. Look at what's in black. Doesn't that look like something right there? And this in black over here, doesn't that look like some sort of definition? V of x plus h minus v of x all over h, and the limit of h goes to 0 of that. Or remember, and this is a limit, so we can take the limit of each grouping. So technically I should have parentheses around this whole thing. And so this is, let's just pull this u of x plus h out. We could do that, remember, with multiplication of limits. We could rewrite the limit of the first times the limit of the second.
Oh, it
actually.
just looks like the difference quotient.
Yeah, it does. I'm sorry. So let me just go back because I might be. So this piece, right, looks like the difference quotient, but if we look at it like this, we're looking at the limit as h goes to 0 of this u of x plus h, right? Just using my rules of limits. This is times the limit as h goes to 0 of this piece, v of x plus h minus v of x all over h, plus, using my rules of limits, the limit as h goes to 0 of this first piece, which is just v of x, times the limit as h goes to 0 of that second piece. And you said it looked like the difference quotient, but when we add that h goes to 0 in front of it, what does that difference quotient change into? That was all a part of the definition of the derivative. Okay, so this right here, this is just the derivative, another way of writing the derivative of v of x. So this is just v prime of x. This one right here, this limit, right, this is just the same thing as writing u prime of x, or u prime, or we could rewrite it as du over dx, depending on which notation we want to use. Let's look at the first limit in front here. So as h goes to 0, this h is going to 0. What are we really left with? We're just left with u of x. So we're just left with the function u of x in front. Plus, if we look at this limit over here, the first piece of the product of the second grouping, the limit as h goes to 0 of v of x. Notice there's no h in that function. And so that would just give me our original function, v of x. And so this was our derivative. This was d dx of u of x times v of x. And so to save room, I'm just going to write u times v, but those are both functions of x. And so this is probably why they might like it writing it this way with that proof. I got it to fall out with the first function times the derivative of the second plus the second function times the derivative of the first. Okay, so that's why we got to use this rule when we're using the product rule, or we have a product of two things. Let me pull out an example. So sometimes we don't have to use the product rule because we can rewrite it so we can use other rules, but sometimes it's helpful to use it too. So if we have y is equal to, let's say parentheses, x squared plus 1 all times x plus 5 plus 1 over x. So let's first do this in the way that we would have done yesterday if we didn't know this product rule, and then let's do it using the product rule. So yesterday we could not have done this without distributing this out. And so let's distribute first before we go through and find the derivative. So if I go through and I distribute my x squared to each term, I get x squared times x is x cubed. X squared times 5, so that's plus 5x squared. X squared times this 1 over x, well that simplifies rules of exponents. X squared over x is just a plus x. And then let's distribute our 1 to each term in the second parentheses. So 1 times x is plus x. 1 times 5, so that's plus 5, and 1 times 1 over x is 1 over x. 1 over x right now, though, I'm going to rewrite differently because we don't know how to take the derivative of that. We need to rewrite it so we can use that general power rule. So we can bring this x up into the numerator by rewriting this as x to the negative 1 power. So I'm going to rewrite this 1 times 1 over x as plus x to the negative 1. Okay, so we've rewritten it. Now we can use that rule of derivatives. 2 of them that we're going to use. We can use our general power rule that says bring our power down front, subtract 1 from our exponent. And we have a sum. Think of x cubed as a function. Think of 5x squared as a function. So we're taking a function plus a function. We can take the derivative of the function plus the derivative of the function. Those are both differentiable everywhere. Only problem we would have is with this 1 over x. It's not differentiable when x is 0. Okay, so we're going to use our rules and just go through. So the derivative of y, so I could rewrite this as y prime. We can rewrite this as dy over dx. And this is equal to, so general power rule, x cubed, bring your power down front, 3x, subtract 1 from our power squared. Plus, so I'm using the rule, I have a constant in front of a function x squared. It's just my constant 5 times, now I use the power rule. So bring down the 2, 5 times 2. So I'm just going to write 10 now. X, subtract 1 from my exponent. It's just a 1. Plus, you get really good at this soon, but the derivative of x is just 1. Bring our power down front, that's 1. X, subtract 1 from our exponent, which isn't shown normally. We get 0. Oops, did I miss something? No, I didn't. I could have combined like terms before I did that, but that's okay. Plus, so derivative of x here, bring my power down front again. I have 1, x to the 0. Derivative of a constant, we saw that rule yesterday, that's 0. And the derivative of our last piece, x to the negative 1. So we're going to bring our negative 1 exponent down, so plus negative 1 x, and we're subtracting 1 from negative 1, so that would give us negative 2. Okay, so let's just clean this up. So we have 3x squared, 10x. I don't see any other term with this than x, so plus 10x. Remember, anything to the 0 power other than 0 is 1. X technically cannot be 0 because it's not in our domain, so we're okay with that. So this is plus 1, so that's plus 2. And then I can rewrite this minus, so this negative exponent on my 2, remember we can make it positive by bringing it down to the denominator. So this is minus 1 over x squared. Okay, you might have thought.
I have a question on that.
Yeah.
So how did you do that last part with the exponent, taking the derivative of the x to the negative 1 power?
Okay, perfect. So let me let's call it, let's look at just that piece. So let's say we have y is equal to x to the negative 1 power. Do you understand how we got that from 1 over x?
Yeah, I do.
Okay. So we're using that general power rule that says that we're going to bring our power down front when we take the derivative. So when we take dy dx, if I bring down negative 1 in front, and then it says take what your original exponent was, which is negative 1, and then subtract 1 from that. And so, well, negative 1 times this, so I don't really need the 1 in there. So this is negative x, and then combining my exponents, negative 1 minus 1 is negative 2. So technically, we don't a lot of times like negative exponents, and they might have let you leave it like that in the book or when you're writing it. But if we want to rewrite this to have a positive exponent, Notice that -2 technically was just the x. And so this -1 stays up in the numerator, and this x to the -2, we bring it down, that changes the sign. And so that can come out here.
Okay.
So I'm seeing like this, I can see where, you know, and again, I'm good at it because I've done it so many years, and I taught algebra so many years because that was one of the things as being part-time for so long, was things that we got as part-timers. But I can see where if you're weak on certain skills in algebra, that could be kind of detrimental in this course, because it kind of piles up on each other. So, but I'm trying to bring them in as we go, and I'm trying to have you guys see those again as you go through those, you know, skills check previous between. Okay, so that was one way to approach it. The other way to approach it was we could have just used this rule. So let me just rewrite this equation out. So we had y is equal to x squared plus 1 all times x plus 5 plus 1 over x. So we technically have two different functions. We have this function u of x, and I'm just going to keep with it up here what I have. So u of x, and this one, let's say, is v of x. So when we take the derivative, so d dx of, and I'm just going to write it like it is in the book, u times v. This is the derivative. I'll do the derivative of the second. So this is the first, which is x squared plus 1 times, so if I don't take the derivative yet, I could write this, and sometimes this is helpful, and we'll see later on, to say d dx of what we're going to take the derivative of, which is this x plus 5. And again, to help us, let's rewrite that 1 over x as x to the -1 power. And then it says plus, in the formula, wherever it went, take our second function, so our second function was this x plus 5 plus 1 over x times the derivative of the first. So d dx means I haven't taken the derivative yet, and with this parentheses is telling you what I'm going to take the derivative of. And it was the derivative of the first, x squared plus 1. Okay, so let's just bring down the x squared plus 1. That was the first, plus, now let's just go through and do the work. The derivative of the second, well, the derivative of x is just 1. The derivative of a constant 5 is 0. And the derivative of this x to the -1. So this is bring our exponent down front, -1, x, subtract 1 from our exponent, -2. Plus the second function, which I'm just going to rewrite what it was originally, x plus 5 plus 1 over x, times the derivative of the second. Okay, so going through and taking the derivative of each piece, the derivative of x squared, bring our power down front, 2x, subtract 1 from our power, so just 2x, plus the derivative of 1, derivative of constant is 0.
So this is like a shortcut, really.
It could be, yeah. Although it depends on what kind of form you want. So now if it really wanted you to have things expanded, because we might want to find when our derivative or if this piece is equal to 0. And so if we want to try to find when this is equal to 0, I'd have to kind of distribute things out and then go. And so maybe, you know, first distributing might be easier. And sometimes it's just a preference. You might see and go about it one way, and I might go about it another way. But you could sometimes it, yeah, totally is so much faster.
So
depending.
both forms of finding derivatives of an equation, right?
Yep. So taking the
Okay.
derivative of equations, yeah. And so, I mean, I could prove to you that this right here is the same thing as this right here by expanding, and I hope if I did that, I would get the same thing. If not, I would have done something wrong with my either distribution and simplifying. So we can do that if you want, but I kind of want to just go through more problems of.
Yeah, you can keep going. It's okay.
Let me see.
Can I
So
see the UV formula one more time?
yeah. So I really, again, so maybe you should do it this way, because I'm going to probably just keep on saying it this way. So let's say if you have y is equal to, and let me go just blow this up so my pen is thicker. So if I say y is equal to some function f, and I usually put the x in there, f of x times g of x, the derivative of y, so y primes, so derivative of the first, f prime of x, times the second, g of x, plus the first, f of x, times the derivative of the second, g prime of x. So you're taking the derivative of one and multiplying it by the original function at the other and summing it. So this is the product rule. So if you had y is equal to 1 plus x squared, all times x to the 3/4 power minus x to the negative 3rd power. Okay, so again, we could go through and we could distribute. We'd have to use rules of exponents, same base, add your exponents. We'd have to get common denominators, etc. But we could go through and use this. So we could think of f of x being our first function, 1 plus x squared. And we can think of g of x being this second parentheses, x to the 3/4 minus x to the negative 3rd. So taking the derivative, by this it says take the derivative of the first. So derivative of the first, I'm not going to write out how I wrote it out before. I'm just going to go through and take it. A derivative of the constant is always 0, and the derivative of x squared. So bring down our power down front, 2, same base x, and subtract 1 from our exponent. So 2 minus 1 is just 1. Times the second function, what we originally had for the second function, x to the 3/4 minus x to the negative 3rd, plus the first function, which was this 1 plus x squared, and then it was times the derivative of the second. The derivative of the second, we got to use that general power rule. So bring our power down front. So that gives us 3/4 x. If it helps you, let's just rewrite it up here. So 3/4 minus 1. That 1 that we're going to have to subtract off is 4/4. Minus, so again, we're going to bring our power down front. So minus a negative 3. And then x we're going to subtract 1 from the negative 3. So negative 3 minus 1. So y prime equals 2x all times x to the 3/4 minus x to the negative 1/3 plus 1 plus x squared all times 3/4 x to the, well, 3/4 minus 1, I'm sorry, 3/4 minus 4/4 is negative 1/4. And then we have a minus a negative, so plus 3x. And negative 3 minus 1 gives us negative 4. And depending on how they ask me, I would leave it like this. Because my problem started with my y values had rational exponents, I would keep it that way. I started with negative exponents in my problem, I would keep it that way. Where that above problem when we started, had that problem was 1 over x to start with. So normally I would rewrite it, and I didn't, with a positive exponent. So this piece I probably would have gone back and rewrote that x to the negative 2 power is the same thing as minus 1 over x squared. So it's really kind of just memorizing that rule, and you're gonna have to do that for the quotient rule also, is memorizing just that rule, and maybe just having it in front of you for a while, all these different rules, so when you're doing the problems, and then hopefully they'll just kind of hammer in your head. Not literally. Derivative of the quotient rule. So unfortunately, we just can't take the derivative of the numerator over the derivative of the denominator. You could do that with limits. We could take the limit of the numerator over the limit of the denominator. You can't do that with derivatives of a rational function. So this is called the quotient rule. So let me just do it my way first. If y is equal to, let's say, some function f of x all over g of x, and f of x and g of x, we have to say are differentiable. G of x, technically, right, it's in the denominator. That function can't equal 0 because it would be undefined. So if this is the case, then the derivative of y, so I'm going to just say y prime, but we can say dy dx, or dy dx, is equal to, okay, so we're taking the derivative of the numerator. So it's going to be f prime of x times the denominator minus the numerator, f of x, times the derivative of the denominator, g prime of x, all over this denominator, g of x, quantity squared. For time's sake, I'm not going to go through that proof, but it is in the book, and it's pretty easy to follow through. And they also use a trick of rewriting something, I think, as a fancy 1 in there, so that they can manipulate it to look like this is the derivative, that the limit of the difference quotient in each piece. Same formula, different notation, just so we get familiar. D dx, if it said they're looking at u over v, oops, u over v, not u over u. So this is saying we're taking the derivative here with respect to x of the function u divided by v. We haven't taken the derivative of it yet. It's telling us that we need to. This is equal to v times du dv. When you see the du, the name of the function, over what the derivative of what we were taking with respect to, that means that is actually the derivative. So that's like the f prime or u prime there. Minus u times dv. So u, that's the first function, times dv. Sorry, this was du dx. I don't know if that just went away. dv over dx, all over v squared. Okay, same thing, just different notation, different letters are representing different functions. I mean, they use v and u, I use f and g.
If I may I butt in and ask something?
Of course.
So I just saw this in a different question. I'm assuming it's fairly similar. When instead of it being u over v and v instead sometimes it's v over u. I'm assuming they just switch places for the most part.
They're just naming the functions differently. So in that case, when they have v over u, they're naming the numerator the function v, and they're naming the denominator function u, where in this case, the derivative, the numerator is called u and the denominator is v. So, but we do have to be careful then which one we're taking the derivative of first. We always take the derivative of the numerator first.
Gotcha.
Yeah, so that could be confusing at first, seeing that. And because it has subtraction here, that's the whole reason why the order matters, where it didn't matter the order for product rule because we had the addition in between. Let's see if I can just crank one out. We haven't learned all the rules yet, but let's see if we can just crank quotient rule out real quick. So I definitely didn't get through as much as I expected or wanted to, but that's not a problem. That happens sometimes, a lot of times. So like in this case, this f of s, this is just saying that I have some function here. Instead of using the variable x, I'm using the variable s. So f of s is just another way of saying the y value of my point. We want to look at the finding the derivative of f of s, which the numerator is the square root of s minus 1, all over the square root of s plus 1. Okay, so that's an s and not a 5. I could see where that could be confusing. So first thing you want to do is you want to rewrite this so that we can use that general power rule. And so we want to rewrite radicals so that they have rational exponents. And so f of s could be rewritten as s raised to the 1/2 power minus 1, all over, and then again, square root of s is s to the 1/2 power plus 1. So taking the derivative, I'm just going to write out the rule real quick. It says you're going to take the derivative of the numerator. So this would be d ds of my numerator, s to the 1/2 minus 1. Notice I haven't taken the derivative yet. This is telling me I need to do that. Times the denominator. So this is s of the 1/2 power plus 1 minus the numerator. The numerator, again, is s to the 1/2 power minus 1 times the derivative of the denominator. So the derivative of the denominator in my case, without taking it yet, so I'm going to rewrite it as d ds of s to the 1/2 power plus 1 all over, it tells me to take my denominator, which is s to the 1/2 plus 1, and square that whole thing. So a lot of times I don't write this step in, I just automatically just take the derivative as I'm writing it. But just as we're going through, and this will help us with different definitions to have this notation and to see it. Plus this would give you partial credit when you're taking the test inside the class if you show me that you do know what you're doing. And then maybe if you got something off, I can give you partial credit. So the derivative of this, this s to 1/2 minus 1. So we bring down our exponent 1/2. S, we subtract 1. So if I subtract 1 from 1/2, 1/2 minus 2/2, that's just a negative 1/2. And then derivative of a constant, -1 is 0, times the denominator, so 6 to the 1/2 plus 1, minus the numerator, don't do anything to it, so 6, it's not 6, s to the 1/2 minus 1, derivative of the denominator, so bring our power down front 1/2, s, subtract 1 from 1/2, so 1/2 minus 2/2 is negative 1/2. Derivative of 1 is 0, all over this denominator squared. So notice we could factor some things out. So sometimes I want you to clean things up. Again, sometimes like if we're going to be looking at graphs of these functions and knowing when that equation or when the derivative, a lot of times it's helpful to find when is that derivative equal to 0. So we'll be looking at that a lot. So being able to do the algebra piece. So it just, and I'm way over time. Not way over time, 1 minute is not way over time. But so you should be able to do that, and if you want, I will continue to just do that real quick and finish that video so you can stay on, but you are welcome to go. But if we pull this out here, this 1/2 right here, s to the negative 1/2, and at the same time, let's bring this down to the denominator and make that a square root. Because remember, square root of s was to the 1/2 power, so this is square root of s. So I just pulled that out. Then I would be left with this blue piece right here. Well, s to the 1/2 power, that's the square root of s plus 1. Minus, well, again, we pulled this piece out, so we're just left with what's this red piece. I need that parentheses there, unfortunately. S to the 1/2 power is the square root of s minus 1. I am not going to distribute the denominator. I'm just going to leave this as the square root of s plus 1 quantity squared. Unfortunately, this is a binomial. I can't just go in and square each piece. That would be wrong. I'd have to FOIL that out. So be careful on that piece. Notice here this negative distributes. So things actually clean up really nicely. So this negative square root of s plus the square root of s inside the second bracket in the numerator cancels. Here we have a positive 1 times a negative 1. So 1 plus 1 is 2. So we have this 1 over 2 square roots of s times, right there is 2, all over this. Oops. 2's cancel. So 1 over the square root of s, all divided by, so technically we could say all divided by with a division symbol, right? And which is the same thing as invert multiplying by the denominator. So all times, flip that up. We have 1 over the square root of s plus 1 squared. So notice all those different forms look so different from one another. Like this is the same thing as this. And so it really depends on how the program wants it when you're simplifying down. Sometimes right now, when we're just trying to figure out the process to do all this, I'm not so worried about you guys factoring and stuff. But those are tools that we're going to have to use in future sections. So I kind of wanted to show you that that's possible. And like I said, I'm not quite sure what my math lab wants on these. But if you ever have a question, is this, right? I'm happy to look over it for you and see it. So I think that is good. I did not finish this section again. I got through most of it. I just haven't looked at taking the derivative of e to the x, which is the easiest one ever. It's just itself e to the x. Derivative of e to the x is just e to the x. But I also wanted to do a couple more problems that kind of extend a little further. And I also wanted to show you another one of those videos like I explained, the 3 blue, 1 brown. And it looks at the geometrical approach of the derivative and really what are we doing here when we look at it. But we'll do that sometime this week, tomorrow or Thursday.
All right. Until next time, I'm off.
Okay, take care.
Mm-hmm.
Thank you guys for bearing with me and letting me finish that problem.